Yuwen Zhang from Succinct is going to be speaking about low latency Ethereum block proving, SP1 and Subblocks. Welcome to the stage, Yuwen.
Hello, everyone hear me? Great. Yeah, my name's Yuwen. I'm here today to talk to you about real-time proving via Subblocks. In particular, you might have heard earlier on the panel, a lot of the teams were talking about how execution was a bottleneck for low latency proving. And I want to give some more context into that, some other strategies you can do to mitigate that, in particular, the Subblock strategy. So I know you guys have heard this a couple times today already, but Ethereum needs to scale the L1 gas limit. There's a plan to do this over the next couple of years, getting to sort of the gigagas regime gradually. And probably the most promising avenue towards this is real-time proving. And at a super high level, again, I don't want to spend too much time on this, but Ethereum's gas today is bottlenecked by validator re-execution. And if instead validators could verify succinct proofs of block execution, that would allow you to pack much more gas in a single block. So at a high level, how do we make an Ethereum block proof using a zkVM? First, you take an existing Ethereum client, such as Reth. You use SP1 or another zkVM to compile it down to some bytecode. In our case, we use RISC-V. And you can execute this bytecode inside the zkVM. And the anatomy of the exact Ethereum block proof, well, there's some pre-flight checks, there's the actual transactions themselves, and there's also some post-execution validation. Now, RISC-V cycles on their own are not super friendly for zero-knowledge proving. So what we need is a kind of intermediate algebraic representation of what happened during these cycles. So the component of our system responsible for generating this intermediate representation is called the executor. And what they do, and the intermediate algebraic representation I was talking about, we call these traces. And traces can be super, super big. For an entire Ethereum execution, the total amount of traces will be hundreds of gigabytes. So what we do, we break the traces up into small pieces. We can prove all the pieces individually using some GPU-accelerated prover. And we can aggregate them together using recursive snark verification into a single constant-size proof. Now, let's think about this from a low latency point of view. So before you can do anything else in generating your proof, you have to generate the first trace. And while you're doing that, you cannot utilize any of your proving technology whatsoever. After you generate the first trace, well, then you can start proving it. But you can't do anything else until you generate the second trace, and so on and so on. Basically, the point I want to make here is that your parallelism is limited by how many traces you can generate at a time. And in other words, the end-to-end latency of your execution, the end-to-end latency of your entire proof is at least as long as the time it takes to generate all the traces. So you can see in this naive approach here, it takes so long to prove, it doesn't even fit on my slide. So yes, basically the most naive but effective approach for generating traces quickly is to optimize the shit out of your executor, which is exactly what we did. We took inspiration from the great engineers at Zisk who pioneered this sort of raw assembly approach. We improved our executor from 50 megahertz in May, 50 million RISC-V cycles per second in May, up to 150 million RISC-V cycles today for our real-time proving demo. And it actually works very well for the 45 million gas limit. But will this scale very well into the future? Moore's law says no, because if you want to run a single-threaded executor, your speed of light is the native performance of your actual hardware's single-threaded CPU. And that hasn't really gotten any better since 2005. So if we really want to scale Ethereum to a gigagas regime, we need to exploit some kind of parallelism. The most correct, future-proof way of doing this would be incorporate some kind of native parallelism into your zkVM. So that would look something like support for a fork syscall or a pthread create syscall. And this is a great idea, but it's not so simple to implement. First, having a non-deterministic executor can kind of mess with different ZKVM's memory arguments. In other words, like proving consistency between different RISC-V cycles. And another problem you might have is that now your execution client has to reason about transactions' data dependencies, which is quite tricky, and you need to get it perfectly correct in order for your proof to be valid. So subblocks are kind of a middle ground. They are quite simple to implement, but they exploit a lot of parallelism, so they're very well suited for the gig gas regime. And the high-level idea is quite simple. You just take your block and you split it up into multiple subblocks of different like consecutive transactions. And how do you resolve this transaction data dependency problem I just mentioned? Outside of the ZKVM, you can have the host hint the output commitment of the first subblock into output state commitment of the first subblock into the input of the second subblock. And you can connect these subblocks in this way. And when you compress all of the individual subblock proofs together into a single constant size proof, you can verify that these hints were in fact consistent. Now, just to drive the point home on how subblocks create super great like parallelism, you have 3 executors running at the exact same time. So after you generate 3 traces at once, you can have 3 provers going at the same time, generating proofs. And also note that each subblock is going to be shorter than your original Ethereum block proof. So not only do you generate more traces at the same time, getting more utilization, your execution portion of your computation also is much shorter. So using subblocks, we were able to achieve 94% of mainnet blocks proven in May 2025. This approach has also received some great adoption from other teams, such as Brevis, who use it today for their real-time proving demo. And we estimate that if using this technique with our current executor technology, we can bring the serial bottleneck of our computation down from 4 to 6 seconds all the way to 1 to 2. So this is a really important latency saving technique that we expect to incorporate well into the future. Yes, that's my talk. If you have any questions, please ask.
Thanks, Yuwen. Yeah, we have a couple of questions here. So in order of popularity, have you considered using block access lists, which will be shipped in Amsterdam, to inform your subblock trace generation?
We have in the past, and in fact, getting the correct abstraction, the correct communication between the host client executor and getting the right inputs into the ZKVM, we think is like a super important future direction. So yes, it is being considered, but no, not in the short term because our really fast executor is doing a great job. Yeah.
Great. Next question. Do the subblock access lists also contain Merkle tree nodes?
Let me go back to my slide. So yes, basically you're asking what is the composition of the storage A, storage B, and yes, they are Merkle tree commitments of the touch state within each subblock. This is a great point to mention that this Merkleization step actually does add a lot of overhead for the subblock technique because you're sort of Merkleizing the same stuff in every preflight and the same stuff in every validation. But yeah, at a high level, that's kind of what's going on.
Why 6% of mainnet blocks have not been proven yet through subblocks?
Well, actually, Brevis did 99.7 with subblocks, so that's pretty good. But in May, our problem was that the longest transaction would take too long to execute. You can sort of think of subblocks as punting the serial bottleneck from the entire execution down to the longest transaction. So that was sort of what was keeping most of those 6% from being really low latency.
Excellent. Thank you so much.
Thank you.